Alright, hello everyone. So, we're starting a new topic, electromagnetic induction and Faraday's law. What is electromagnetic induction? Well, before that, let's see what are the topics we're going to discuss. Electromagnetic induction, Faraday's law, and something called Lenz's law. Electromotive force, or electromagnetic induction, or electromagnetism induced in a moving conductor, how generators work, some other topics like back EMF and counter torque, transformers, another useful electrical device, and how electricity is transmitted, and few more topics and more applications. Applications of this induction, production of current, how it's been applied in sound systems and other stuff. GFCI, it's a electrical component in households. It's a safety device, ground fault circuit interrupter. So, going back, electromagnetic induction. Now we've been talking about how to produce magnetism using electricity, right? So when there's current in a wire, there's magnetic fields around it. We know the reason is the motion of charged particles. When charge is moving, it produces magnetism. So we can use, just as the most simplest case is a single straight wire, and if there's current through the wire, it creates a magnetic field around it. If you want to enhance it, you can make a coil, a loop out of it, so that kind of increase the strength of that magnetic field in the middle. And if you want to have even more magnetic field, you make a coil, like number of loops, couple of loops. That way you have a stronger electromagnet. So what we've been discussing so far was how to produce magnetism using electricity. Now in this chapter we're going to discuss the opposite. How to produce electricity using magnets. And that is called electromagnetic induction. And an important rule, that a principle that explains how this works is called Faraday's law, developed by probably like 2 centuries ago by a scientist named Michael Faraday. So we already saw the topics we're going to discuss, and let's see how this thing works. Okay. So 200 years ago, Faraday looked for evidence that magnetic field would induce means producing it, an electric current with this apparatus. So what he did was, he observed that, let's say you have a wire, and when you make a loop out of it like this, and then you take a magnet and south, and then you move this magnet back and forth in the vicinity of this coil, and the other side of the coil he connected it to a meter. Now, we have modern digital voltmeters. That time Faraday didn't have that. He had an old-fashioned analog meter. There's a little scale or a needle goes back and forth when there's current. So what he saw was, when you move a magnet next to a coil, there's deflection. The needle moves. That means there's current in the coil. So if you just bring the magnet close to the coil, if you just place it next to it without moving it, no electricity. You have to have some kind of motion. It could be either the magnet moving, it could be either the coil moving, or it could be both. What you have to have is a relative movement between the magnet and the coil. So that was his first observation. When there's motion, relative motion, better word is relative motion between the coil and the magnet, there's electricity. Number two, we saw that faster the motion, more current. So faster the motion, there's more current. We also saw that stronger the magnet, there'll be more current. More number of loops the coil has, there'll be more current. Also, the direction of the current depends on which way the magnet is going. If a north pole is coming towards the coil, the current will flow in one direction. If the north pole is going away from the coil, the current will switch the direction and will start flowing the other direction. If you bring a south pole in, current goes in one direction. If you take the south pole away, current switch the direction. So the amount of current, how to produce the current, you have to have a relative motion. The amount of current produced depends on the magnetic field, the coil, and how fast you move it back and forth. Direction of the current depends on which way, which pole, north pole or south pole, which one coming in or whether it's going back. So it depends on the type of the pole and which way it's moving. So this was a very interesting observation. He realized that you can produce electricity. All this time, the electricity was produced using mechanical reactions, right? Like electric batteries. Now here's another way. Sorry, not mechanical reactions, chemical reactions. Now here's a new way of producing electricity. You don't need any chemicals. You just need a magnetic field and a coil and a relative movement between them. So this is the beginning of the idea of electric dynamos, right? The electric generators, where mechanical movement, motion, produces electricity. So that is a breakthrough actually. That's how we produce electricity in this country, pretty much throughout the world, unless you use solar panels or just chemical batteries. So the motion of a magnetic field or the changing magnetic field in the vicinity of a coil produces electricity, and this is called electromagnetic induction. So we'll look into some details. What are the factors that determine? So things to keep in mind. You have to have relative motion, right? So this is one. It depends on the speed, how these things move. Like you can move the magnet or you can move the coil. So the relative speed between them. Or you can say the rate of change. The rate of change. It could be the magnet is moving, it could be the coil moving, it could be both moving. So as long as something is moving, rate of change, faster it moves, more electricity, more voltage you can produce, more current you can produce. It depends on the coil area. So instead of moving the magnet, imagine you change the area of the coil. Like you have a circular coil like this. You can compress it and make it look more like this. You can stretch it, make it look more like this, right? You're changing the area back and forth, make it smaller and bigger. So that way also you're changing something, right? That produces voltage or current. So I keep saying voltage or current. So what is happening here? It actually induces a voltage. That voltage makes a current in the coil. Now, if the coil is connected to something, like if there's a light bulb or something is connected to that, that voltage will drive some current through the circuit, and the amount of current you get depends on how much resistance in the circuit. But yeah, when you make changes, it produces voltage. So, to explain all these, Faraday came up with some ideas. First of all, he defined something called the flux. When you change the flux, you create electricity. Okay, so let's see what other slides we have. Okay, before getting to the next slide, let's understand what magnetic flux is. So, imagine you have a magnet, north and south. So the magnetic field lines, we know that it's coming out from the North Pole and then circles around and goes back to the South Pole. Now here we have a coil. We place a coil in front of this. So these magnetic field lines are going through the coil. Now if you move the magnet back and forth, the magnetic field through the coil changes. If you move the coil, the same thing, the magnetic field changes. So the flux is actually, or if I like change the shape of this coil, if I compress this, if I stretch it, the area of the coil changes. So the amount of voltage induces in this process depends on how much magnetic field goes through it and what is the effective area of this coil that magnetic field is going through. So it defines something called flux, which is equals to B times area, right? So if I change the magnetic field, flux changes. If I change the area, flux changes. If I change both, flux changes. So we define this magnetic flux in order to simplify this changing process, right? Later in the slide, you'll see that we define this flux as the integration of B dot A. If you know calculus, this is another way of representing that. But for our purpose, we can just say flux is B times A. The magnetic field multiplied by the area it goes through. The unit for flux is given by, it's called Weber, WB, right? Unit is Weber. Okay, so for an example, if I say there's a magnetic field of 2 Tesla, magnetic field of 2 Tesla, going through an area of 3 meters squared. What's the flux? It's B times A, so 2 times 3, 6 Webers. Right, so that's how you find the flux. There's one more important thing. Here we place this area completely perpendicular to the incoming magnetic field. If this is the magnetic field and you place the area completely perpendicular to that, yes, you get this entire full flux. If you place it parallel to this, if it is parallel, zero flux because it's parallel to the magnetic field, so it just slides over it, nothing, right? If it is at some angle, you have to get the perpendicular component. So we'll come to that in a minute. What you need to understand is to have the maximum flux, the area has to be perpendicular. Okay, so moving on. So here we see that these ideas we just mentioned, magnetic flux. If it is at an angle, you have to get the perpendicular component. So, okay, let me erase this. How do we explain this? Now, where do we define an angle, a theta, to make this work? So, here's the magnetic field lines. If you place the coil completely parallel, flux has to be 0. So this is what we do. This time, instead of sine, we're going to go with cosine. To do that, I mentioned this in our previous discussion. We define something called the area vector, a line perpendicular to the area, and we measure the angle between that and the magnetic field. So over here it's 90 degrees. So theta equals 90. So we define the flux as BA cosine theta. So if theta is 90, cosine 90, cosine theta is 0, flux becomes 0. When you have it perpendicular like this, area vector is parallel to the magnetic field. So, theta is 0. Cosine theta, cos 0 is 1. So, flux is BA cosine theta, just B times A, gives you the max flux. If it is at an angle, like this, you measure the angle, whatever that angle between that, take the cosine and solve for flux, right? Okay, so now going back to electromagnetic induction, what Faraday said was, what he experimentally observed was, when magnetic field or the area or something is changing, produces electricity. And then he simplified this and said, when flux is changing, electricity, voltage can be produced. Remember this symbol over here? EMF symbol, right? EMF, electromotive force, or in other words, just voltage. So when flux is changing, voltage produced. Now the amount of voltage depends on how fast the flux is changing. So mathematically we say that E equals to d psi by dt. Mathematically this means the rate of change of flux. Now some of you probably haven't taken calculus, so you may be not familiar with this particular way of writing. This means the rate of change of flux. The same thing you can write as delta psi over time. The amount of flux change during a given time. You can put a delta t here. Or in simple terms you can say psi divided by t. So voltage induced, electricity produced is equals to the rate of change of flux. How fast the flux is changing. Faster it change, more electricity it produces. Now this is for a single coil. Let's say you have a magnet and here's the magnetic field coming out. Now pole, you place a coil like this, just one loop, a single loop you place, and you calculate psi, which is BA, and then you change the magnetic field. How do you change it? You can take the magnet completely away. So at one point psi was BA. After some time psi is 0 because you took the magnet away. Now flux has changed from this initial to this final, right? It has changed. That change divided by how long it took us to remove that magnetic field. That's the time interval. Dividing one by the other, you can find how much voltage was produced. Now instead of a single loop, if I put multiple loops, n number of loops, now you can say psi equals n times psi over t, or better, n times d psi by dt, using some calculus. Now there is a negative sign in this equation. What does this negative sign means? Now up to this is Faraday's law, right? This part, These are all Faraday's law. Voltage equals magnetic flux divided by time, or change in magnetic flux divided by time, or the rate of change of magnetic flux. That's Faraday's law. What is this negative sign? This is Lenz's law. Negative sign comes from Lenz's law. What Lenz said was, whenever there's a, so he was after Faraday. So Faraday developed the main theory and Lenz kind of polished it, right? So what he said was, okay, when you change something, when you change the magnetic field or area, or when you change the flux, produces electricity. That voltage, that electricity you are producing is always opposing the initial change. Opposing the initial change. What is this opposing thing? We'll come to that little later when we are moving forward. You can think of something like you are moving a magnet to the left, the coil try to push it away from it. You try to move the magnet away from the coil will produce a magnetic field to pull it back. So actually this is what happens. When you are bringing a magnet in, you are increasing the magnetic field inside the coil. Coil tries to oppose that. Coil will try to produce its own magnetic field to oppose this incoming magnetic field. Let's say you are pulling the magnet out, the coil will try to oppose that. It will produce its own magnetic field and try to pull it back. That's how the nature works. You try to change something, the other party opposes it. So this whole opposing thing determines which way the current is moving in the circuit. So to indicate that, Lenz put a negative sign in the equation. So that's the whole idea. When you change the flux, EMF or voltage produces in such a way to oppose the initial change, right? So that's how we explain Faraday's law. Okay, so let's move on and see what else we have. Okay, here's a problem. Here's a math problem. This will help us understand what's going on here. Let's see what we have. Loop of wire in a magnetic field. So I believe you guys took time to read this and give it a try. So you already gave it a try. You probably have the answers by now, but let's see how to solve this. Okay, so here we have a square loop of wire. Each side is 5 centimeters. Is in a uniform magnetic field. So this time we'll put the magnetic field going into the board or into the screen. Right, because if I put the coil like this and draw the magnetic field like this, it's parallel to it and it won't do anything, so that's kind of useless. So now the magnetic field is perpendicularly going through it. So B field is 0.16 Tesla. What is the magnetic flux in the loop? B times A, 0.16 times the area. So area is 5 by 5, but it's centimeters. So 0.16, let's do the math. 6 multiplied by 0.05 square gives me 4 times 1, 2, 3, 4. 4 times 10 to the negative 4. 4 Weber, right? So that is the flux. When B is, okay, so this has a couple of parts. When B is perpendicular to the face of the loop, like how we have it, when it is perpendicular. So if you think about a side view, right, here's a coil, here's the loop, here's the electric magnetic field, like how I have it in the above diagram. Let's say this is perpendicular, so we get this answer. Now I can redraw the same thing. I try to give you guys an idea of, now if it is perpendicular, it's going to be like this, right? This is perpendicular. Now if it is not perpendicular, if it is making a 30-degree angle, it will be something like either this way or it will be like this way, as this area vector making 30 degrees, 30. So what happens? Flux is BA cosine theta. So that will be, this is BA 4 times 10 to the negative 4, that's BA cosine 30. We multiply this with cos 30, multiply by cosine 30, that gives you 3.46. 10 to the negative 4 Webers. What is the magnitude of the average current in the loop if it has a resistance of this many ohms and is rotated from position B to position A? Okay, so this is position B. It was at 30 degrees. This is position A. It's at 90 degrees. Alright, so it's asking what is the magnitude of the current. So it's asking current. Before finding the current, we can go with Faraday's law and find the voltage it produced. This equals N delta psi by delta T. Now, to find the number, you don't need the negative sign. Negative sign only tells you that whatever you produce is against what you are trying to do, right? It really doesn't, you don't need that to find the voltage. So don't worry about the negative sign in calculation. The equation has a negative sign, so you need to know that, like, to have a complete understanding, you need to know this equation has a negative sign. Comes from Lenz's law. Doesn't affect your calculation. So for the math part, do it without the negative sign. So the voltage it produces is number of loops times the change in flux over time. So it's a single loop, so N is 1. So this is just psi over delta T. So it rotated to this position in 0.4 seconds. So the time it took, let's write all that over here, time is 0.14 seconds. What's the flux change? Flux initial, it goes from B to A, right? So it starts here, it ends here. Initial flux 3.46 10 to the negative 4. Flux final 4 times 10 to the negative 4. Delta flux, flux final minus flux initial. 4 times 10 to the negative 4 minus 3.46 10 to the negative 4. What do you have? 54, right? 0.54 10 to the negative 4 Weber. That's the flux change happen in this time interval. So dψ by dt, flux change 10 to the negative 4 divided by 0.14. What do you get? 1 second. So what do we have? 0.54 divided by 0.14 gives me 3.8 times 10 to the negative 4 volts. This is a voltage. So we have the voltage. It's asking the current. To ask current, we need to know, to find current, we need to know the resistance. Now this coil is, in this case, you can say, okay, there's a resistor in this coil. So when there's voltage, there will be some current because there's a resistor, right? So how do you find the current? It will be V over R. 3.8 times 10 to the negative 4. It's going to be a very small current divided by it's a small voltage. So what do we have? We divide by 0.012. Made a mistake, I guess. About 30 milliamperes. 0.030, something like this. Amps or 30 milliamps. Okay, so it's the video is already half an hour, so I don't want to take too much time. Let's see what else. All right, here's Lenz's law in a proper sentence, but you will get familiar with this when we go over this in class again and again. I'll show you some few more stuff, conceptual things. Magnetic flux, you can change it by changing the area of the coil. Now, here's an interesting thing. There's a magnetic field going into the board. We have a coil and there's a magnetic field going into it. When you stretch it, it says current goes clockwise. Alright, how do you figure that out? Why it's clockwise? So these are some conceptual things I want you to think about. Think about this opposing nature. What makes it move in the clockwise direction? We'll go over this in class. It's easier, use right hand rule and all that. Here's another way. Instead of changing the shape of the coil or changing the magnetic field, very easily we can rotate the coil. When the coil is rotating again, the effective area between the coil and the magnetic field changes, or the flux changes. This is the most easiest way of producing electricity. You have a fixed magnetic field, you have a fixed size coil, the area is fixed, but you rotate it in the magnetic field. Flux changes, you produce electricity, and this is the principle of electric generators or dynamos, right? In reality, we have these huge magnets, there's huge coils in between, and you use some kind of mechanical force. It could be a wind turbine that rotates the fan, that rotates the coil inside, producing electricity. It could be the motion of water, like you have a reservoir somewhere up in a hill, and then water comes down really fast, hits a fan, rotates it, produces electricity. That's how all these hydropower stations work. Or it could be, even in a nuclear power station, this is the working principle. You use nuclear reactions to produce heat. That heat boils water, creates steam. Steam goes through tubes and hits a fan and rotates the coil. So everything comes down to rotating a coil in a magnetic field, right? Induction stove, another good example. So I'm briefly going over a few examples, but we will talk about these things in detail. Okay? Alright, thanks.